Hello and welcome to this supplementary episode of Code Space. Last week we promised to make you a genetic algorithm program, right? So the idea was that we would have a bunch of balls or orbs, figure out a way to make it to a target. Now how they would figure out would be determined by the genetic algorithm. We felt that that episode would have been too long, as in we would have to program the orb, it responding to gravity, having motion, left and right motion, reaching a target, all of those things you would have to program. And on top of that, you'll also have to put in the genetic algorithm. So that episode would have been too long, and I thought it would be appropriate if I can just make a very simple physics system as a supplementary and have the main video just concentrate on the genetic algorithm part of it. So that's about it. Let's get cracking. Let me just show you what I mean by what I meant to actually program. All right. So what I'm showing on the screen is just a simple drawing. The idea was that I would have like a canvas or something, and on this canvas I would have a target over here. Okay, let's just make this point as the target. Now, you would have a bunch of balls and everything. Just initially the balls would be, let me just undo this. All right, so let's say I have many orbs or balls. I'm torn between calling this either an orb or a ball. I'm going to go with orb. The reason for that is because there's too many balls on the internet as it is. All right, so I'm just going to call it orb. Now these orbs have to figure out a way they would fall down essentially, just like how orbs respond to gravity. They would fall down to the ground. They would be on the ground, and they would figure out a way to make it to the target. That's the idea that I'm proposing over here. All right, so that being said, let's just go ahead and get cracking on this one. All right, let's just make the very simple physics system required to handle this. All right, I already have the index.html file set, and what index.html has is just a very simple canvas, a canvas with 900 to 400 as its dimensions. I also have a JavaScript file called as the physics.js. it's just I'm just calling it sphysics.js. All of the source code and everything, I'll put it in the description. It's available for you to play with, to download and play with. All right. It has an init function. The init function essentially gets the canvas, creates the context out of it. And if you remember our episodes from previous weeks, we had always made these width and heights as constant. But in this case, we are actually getting the width and height from the canvas itself. All right, so they have these values. So let's just see what this looks like on the screen. This is what it looked like. And if I was to say is equal to console.log width, the variable that is still held in the context of the JavaScript, you would see that it still says 900, which is exactly the width that we set in the index.html. All right. That being said, let's just go and create our orbs. All right. So how do we create our orbs? Instead of actually putting it on the same file, what I wanted to do was create this orb as a class by itself. All right. Orbs exist as classes by themselves. And I think it is most appropriate if I have them as their own separate JavaScript files. All right. So let's just create a new JavaScript file and we'll call it orb.js. Orb.js essentially just has a class called orb. In JavaScript, you create classes exactly the way you create classes in, let's say, Java or what other language? C++. All right. I also keep in mind that I'm going to continue to use the CodeSpace API that we've been developing for weeks. It has very simple functions in it. It has a way to basically capture a point. It has a map function, a distance function, and some such. All right. So that being said, so we have an orb. So what things do orbs have, or balls? All right. So if these things have to exist in an environment, what properties should they have? They should have an X and Y location, basically where they are on the screen. So let's just define that. So I'm going to call a constructor, an empty constructor for now, and this constructor will have this dot So I'm just going to call it this dot position is equal to new point, and it will have a random point, right? It should have, I mean, it should be created at a random location. Let's see, or we leave it to the system that is creating this orb to provide the x and the y location. So we'll say x comma y, x comma y. All right. An orb will also have a force that is acting on it. Now, force appends or adds to the motion of the orb, and this motion essentially has velocity associated with it. All right. So we'll just create another variable called velocity, and we'll make velocity also a point. We'll make velocity also a point. And for now, let's not give anything to the velocity, but it's essentially just a point. So instead of having 4 variables, having x and y location and x and y forces, x and y forces, we have position as a point and velocity as a point. Even though they both are using the same point classes, they are both having different contexts, wherein the position variable essentially is the position, and velocity is essentially how much force or how much you have to change the position by. All right. So now I have a constructor which basically creates the position and the velocity. Let's also have a function called add force. Now, what does the add force do? And it will create, I mean, it has a parameter called force. What does the add force do? It essentially adds to the velocity. All right. So let's just let me just look up exactly what the definition is. Yes. So it basically adds to the velocity. So I can say this dot velocity dot x is equal to force dot x. Now force is also, I'm also expecting force to be a point. All right. So this dot so this dot velocity dot x is equal to force dot x, and this dot velocity dot y is equal to force dot y. All right, that's that's it. Do I have to say function? No, I actually do not have to say function. When you are creating a class, I can just say add force. So that essentially is how you create a function. So yeah, so that's about it. And then what? So an or also requires something called as an update function. Now, what is this update function? We'll find out what an update function is. Or instead of that, let's just go to the S physics and start drawing our balls, right? So first things first, we have to include orb.js in the HTML file. So I'll just say orb.js. So I have that, I have the physics.js, now I have the physics. I can just go ahead and start creating orbs. Let's see what it looks like. Orb is equal to new orb. Remember, it requires an x and y location. What x and y location? Let's just give it a random x and y location. I can say that. Remember the random between, it's exactly what it means. Give me a random number between a minimum and a maximum. Say, give me a random number between, let's say, so this is x and y. So on the x, I'm going to keep the x as a constant. I'm just going to say, give me 10. All right, or create the ball at location 10. And I'll just say y, random between 0 comma height. All right, what is this 0 comma height? Which means a random position between 0 comma height, a random location between the 0 and height of the width. So I have that going on. All right. Now, how do I draw this orb? I can say gravity context. So why am I calling it gravity context? All right. I've decided on the name. That's what it is going to be. So gravity context. How do I draw, let's say, an ellipse? Let's just look at the reference that we have. I know it's the arc function, but I just want to make sure. Yes, it is the arc function. Where is it? All right, so there it is. So that's the arc function. All right, so that's how you add something. So gravity system. So yeah, this context dot arc. Do I specify a fill? Let's just give it a fill color. Dot fill style is equal to let's just say RGB 10 comma 100 comma 100. All right, so this should be roughly RGB cyan color. It should be roughly cyan color. Arc. Make an arc at the orb's x location. Oh, I'm sorry, it should be position. Position dot x orb dot position dot y. Radius. What? Oh, all orbs are also supposed to have a radius. We forgot to create that. For now, let's just make it 10. All right. So we forgot to make radius as a constant. Now the thing about this is I want to make all of the orbs or balls that I create have a constant radius. Now, if you are programming this, you are more than welcome to make them you know, variable length or variable having variable radius. All right, so start angle is always 0 and end angle is math dot pi into 2. Remember, a full circle is 360 degrees or 2 pi. All right, so yeah, look, anti-clockwise or clockwise, I really don't care. So yeah, so that being said, let's see if I say graph, I have to say dot begin path and then let's make it fill, right? So what is that? Fill, right? Not fill. Let's see what it looks like. This should. All right. So obviously there is some error. Oh, there's no error, but hold on. All right. What am I missing? So we do get there. Is it begin path or? Yeah, it is begin path and then you do a fill. Oh, yeah, look at this. Orb 10 comma y. I forgot to give this. I forgot to give the y location. I think it was because it was undefined. All right, so there you go. So that's what an orb is supposed to look like. All right, it is a little bit too small. We'll fix all of that. All right, so now we're going to create many orbs, right? So we'll have the orb maintain its own color, not just the color. We'll also have the have the orb maintain its own radius. All right, so we'll just go back to the orb.js and we'll say we'll first create the constants. We'll say all orbs must have a radius of let's say 20. Yeah, 20 is fine. And all orbs must also maintain their own color. They are responsible for their own color. All right, so I can say this dot color is equal to RGB of random between. I want to make them a little bit, it doesn't matter actually. So I'm just going to say 10 to 250 and I'm going to do a parse int over here. The reason why I'm doing a parse int is because it will return a value between 10 and 250 and it will have decimal places. So parse int ensures that it is essentially an integer. All right, so I have. So so that was red. This is green, and here you go. This is blue. All right. Let's also give it an alpha. All right. What is alpha? It is essentially transparency. I'm going to make them 50% transparent. So now they have a radius, they have a color. And remember in the S physics system how the environment itself was responsible for drawing the orbs. Let's make the orbs responsible for drawing themselves. All right. So I know this sort of breaks the single responsibility principle, but for the sake of convenience, we'll just create a function called render, to which we will pass a variable called context. So we'll pass the context and we'll make it responsible for drawing itself. So there you go. So there you go. So you have fill style is equal to what? This dot color, right? Yeah, it should be this dot color, begin path, this dot position dot x, this dot position dot y, this dot radius, and then you have math dot pi into 2. So this can also be a constant. The reason why I'm going to make this a constant is because it's a piece of math that is getting calculated over and over again. So just to provide some respite to our processor, we'll just say this dot 2 pi is equal to 22. So now it is a constant. All right. Oh, you know what? It's actually not a constant, and the reason for that is because this is not a static variable in the classics. This is not a static variable like you have in Java. This is still initialized for every orb that you create, but at least it won't be calculated for every time you draw the orb itself. All right. So there you go. So now you have an orb that has a constructor. It has a way to add force, which we have not used yet, but that's fine. Then we have a render function, which means the orb is responsible for drawing itself on the screen. All right. So we go back to the. So we go back. We say orb dot render. There you go. Now let's see what happens. Yeah, there you go. So that's what it looks like. All right. So it is now essentially rendered on the screen. It should be a random color every time I refresh. So there you go. It is a random color. All right. Once again, what is, let's make it 25. All right. So random y position every time that it is created. All right, so I've created the ball. So now what? This is not doing anything. All right, let's add gravity to it. All right, so how do I do that? So what I'm going to do is just say orb dot add force, and before I do that, I'm going to create a constant. All right, why constant? Because I'm going to create a constant which is essentially determining how strong gravity is. So let's just create that. So constant, and say gravity is equal to, what is gravity? Gravity is essentially a force that pulls you downwards or in the y direction. So constant gravity is equal to, I'm going to say 9.8. What 9.8? Because that's Earth's gravity, right? 9.8 meters per second square. So there you have it. So I'm going to say orb dot add force, or let's just create gravity as a point force itself. Say new point, you say 0, 9.8. Why 0, 9.8? Because 0 means there is no force on the x direction. There is only force on the y dimension. All right. So I'll just say, instead of creating a new point every time, just say add force gravity, and then orb dot render. Let's see what happens, shall we? Nothing happens. Nothing happens. Why? Because we have not animated it. We've said add force once, but we've not animated it, right? So let's just do that. Let's create a function. So we have the init function, and let's create it afterwards. So function animate. All right. So what does the animate do? It will say, and before we do that, let's create the orb. Variable orb is equal to new orb of this location, comma y position. The animate function is going to say orb dot render. Basically, it is the one that is responsible for rendering itself. And the animate function is also going to add the gravity force on every time the animate is called. All right. Now JavaScript has many functions to essentially perform animation. There is the set timeout, there is the set interval. There's also something called as the request animation frame. The request animation frame will essentially give us or return us back to the function that it is being called whenever the next frame is available. So it's essentially as fast as possible. So let's just say request animation frame of animate. So request animation frame of, we provide a callback function. Now the callback function essentially just calls itself back and it should render. All right. So now that I have said add force and I have said render, would it animate? Let's find out. No, it won't animate yet because I've not called the animate function the first time. But let's do that. So I have the in function. I'm calling the animate, which should essentially add the force. Add the force to its velocity, but would it do something? Let's find out. Once again, nothing. Why? Because even though we have a velocity, the velocity doesn't translate to a change in its position. All right. So how do we do that? So we can either change the position in the animate function of this one, or we can create a function over here, and in this case I'm just going to call it update. What does update do? Update essentially updates the current position of the orb to its velocity. All right. So this dot position dot x plus is equal to this dot velocity dot x, this dot position dot y is equal to this dot velocity dot y. So that's what the update function will do. All right. So the adding a force would mean change to its velocity, and update will basically change its position based on the velocity that it has. All right. And where do we call the update? We'll call the update from the animate function. All right. So it's basically calling the update, meaning update my positions right now. All right. So I have a certain already existing position. I have a velocity. Update my position to the velocity. That's what the update function means. Let's see if that made any difference. Actually, it did. It did. Oh. All right. And the reason why you're seeing this streak over here is because we're not basically clearing the canvas. And so let's just do that. So we'll say grv context. Hey, hold on. We're not passing the context line. grv context. Then how the hell was it working? Oh, yeah. That's because, wow, I have to be careful with these variable names. So I was essentially referencing the gravity context from within the render of the orb class. I shouldn't be doing that because the render expects a context to be passed. And now that we've passed that context, we need to pass the context from over here. All right, so clearing the rectangle. So we'll say clear rect from 0, comma 0, oh come on, to width, comma height. Now let's see what happens. All right. All right. You can see the force being, yeah. So I did put 9.8, which is actually quite a lot of gravity that is being added to this specific orb. All right. So now let's just let me not give a random point. Instead we'll just say start from 20. All right. Now let's see what happens. Now gravity is an additive force. All right. So basically what that means is that gravity is a constant force. The force is constant throughout the life of the orb, just like how it is in real life. Right now, sitting in this desk, all of us sitting in this desk, I am feeling the effects of gravity. So are you, sitting or standing wherever you are. You're feeling the effect of gravity being pulled down on you constantly. So therefore, it should be a constant thing that happens. So the force should be added constantly. All right. However, what I'm seeing is that the speed of this orb doesn't increase. Should I call it on the update? Should I call it on the update? Because I'm not seeing it increase. What happens if I was to make this 0.8? All right, I'm going to print out velocity and just see what happens. All right, so I have the force that is added to the velocity, and the velocity is added to the position. I'm just going to print out velocity. No, it's a I mean, it looks like it's a constant force, all right, but it is not a constant force. It is an ever increasing force, all right. So even in the update, velocity does not seem to have increased. Why not? Oh, it's not velocity equal to, it's velocity plus equal to force. All right, so there we go. So then now it should be, now what? You have point, which is 0, 0.8, which means nothing in the x direction. But when you add it, (20 and 25) orb, so velocity, and then velocity goes back and adds. I'm going to remove this for just a second. So yeah, so force adds to the velocity, and position, and velocity adds to the position. All right, so that's how it should work. Now that I have, okay. Instead of request animation frame, just going to require a little bit more. Control set time. Alrighty, come on. Yeah, you know, that's the process essentially. I swear it'll be something very silly. All right, let's see what it was. All right, so it's always NaN, which means it's not a number. Why not? Why is it NaN? Is something happening here? Oh, you know what? Because velocity is not initialized. I have to initialize velocity as 0, 0. That's what was happening. I told you it is silly. So yeah, so like I said, it is a process, and this essentially needs to be, you know, this is the process of development. A lot of, all right. Now look at the ball that's like falling. So every frame it increases its speed. All right. So let's just go back to request animation frame and see what it looks like. Oh, that was too hard. It was too hard, right? I mean, you can see that it was actually too powerful, right? Right. I mean, gravity is such a force that it's a continuous force, and it acts continuously. So therefore, it will. The orb is going to accelerate as fast as it can, unless we specify that all of the orbs have something called as terminal velocity, right? If I was to if you were to bungee, if you were to jump from a plane, you know, recreationally, you wouldn't fall as fast as possible. You wouldn't fall. Your speed wouldn't increase to infinity. It would, in fact, be, you would have air resistance and all of those things going. So that was what is going to happen to the orb as well, right? So we are going to set the upper limit of the velocity to something, to an arbitrary value. All right. So what is its maximum velocity? Let's just determine that. I'm just going to move these so that constants are in one location, everything else is on the other. What is its, I'm going to say maximum velocity, we'll say 5. All right, 5 in either direction. Right, whether it is the x or the y, the maximum velocity that we are allowing for an orb to travel is, let's say, 5 pixels per click. So Is it 5 or do you think 8 would be appropriate? No, let's just leave it at 5 and see what happens. All right, so I have the update. Before I do the update, I will say if this dot velocity dot x is greater than max velocity, this dot max velocity, then this dot velocity dot x is equal to this dot max velocity, right? So we are binding the x, we are binding the y as well. If y is greater than max velocity, then y is equal to velocity. Now remember, they can also go in the reverse direction. So eventually they're going to have this arc bounce back up. During the bounce back up, or when we add some other force to it, we want to ensure that it is bound even in that case. All right. So how do we do that? We can say if x is less than negative of max velocity, then this dot x is equal to negative max velocity. The same goes for y as well. If this dot y is less than or equal or less than negative of max velocity, then this dot y is equal to this negative of max velocity. Now let's see what it looks like. Oh, we just gave 5 and I don't think it's too fast. I'm going to make it, I wanted to make it double and make it 10, but I'm going to split the difference, say 8. All right, so 8 is like the maximum velocity allowed for an orb to travel on the screen. All right, yeah, so that being said, what about bouncing? It has to bounce on the environment, right? So how do I do that? Let's do that. So now that I have added the x and the y position, I say if this dot position dot x is greater than width, right? I mean, if the orb, so you have an orb, if it moves, is it okay if I basically showed it here? All right, I'm going to just create a new one. These things take such a long time to do, but you know, it's a process and we are going to, we'll just live with this. That's all right. So this was the canvas and let's say this is now our orb. All right. So so an orb can essentially, we want to make sure that if the orb goes more than this, we bounce it back in this direction. If it goes beyond over here, then we bounce it back in this direction. We also have to make sure that it remains in bounds in the y direction also, and the same process happens. Make sure that the orb essentially bounces against all of the walls. So we are just doing the wall physics right now. All right, let's do that. The wall physics. So now I have position is greater than width, or if this dot position dot x is less than 0, 0 being the left side of the canvas, we'll say this dot velocity dot x into equal to -1. All right, so this essentially reverses the x direction. All right, so we'll just leave it like this and just see what happens. We'll do the same thing with the y location, y also. If y is greater than height, and if y is less than 0, then velocity dot y is equal to, into equal to -1, which is basically reversing the velocity direction. Now let's see what it looks like. Poink. You see that it goes below the screen, right? It goes below the screen. That's what happens when you have, that's what happens when you work with canvases, essentially. So what happens is the orb has essentially gone below the screen, but this specific condition that you see over here executes over and over again, bringing the orb just a little bit above, but also a little bit down, above and down. So that process keeps happening and it essentially messes up the physics. So when we detect that the velocity, that the position has gone, beyond the width or the x, what we'll do is we'll just set its position back to wherever it was previously. So we'll say if it is greater than width, if this dot position dot x is greater than width, then we'll say this dot position dot x is equal to width, and we'll do the same in the other direction also. If this dot position is less than 0, then this dot is equal to 0. All right, and we'll do the same with height as well. We'll do the same in the y direction as well. This dot position dot y is greater than height, then y is equal to height, and if y becomes less than 0, if it goes above, then y is equal to 0. All right, so now you'll have some semblance of bouncing going on. Let's see. All right. Oh, now what happened? I've probably messed up something. Why is, if it is greater than height, then it is height. If it is less than 0, then y is equal to 0. Yeah. Yeah. I would have expected it to just go all the way back up, but I am not entirely sure why it is doing this. So let's just find out why. If it is greater than height, or if position dot y is less than 0, then n2 equal to -1. If it is greater than height, then let's do this other thing. I'm taking it outside of the loop, outside of the if condition, because I think that makes more sense. Let's see what happens now. Oh, come on. Yeah, I mean, I would have not expected it to bounce in that manner, but let's see what happens. I'm just going to log the y, and hopefully it's not too many log statements. It's not too fast. Oh, it's because gravity is a force that is constantly acting on it. Of course it is like this. Of course it is like this. Because gravity is a force that is constantly acting on it, right? So the ball, of course it wants to go all the way back up, but it can't because gravity is still acting on it. So that's why you see this bounce that is going on. And that particular thing is a happy medium that it sees. All right. Now you can see that the bounce does happen, but the bounce is happening in such a way. Oh, you know what? Let's just give this system, or let's just give this odd an x force also. Let's say add force, new point, make it 2.5, 0. Now look at this. I'm adding the force only once on the x direction. Only once. Why am I adding it only once? Because it's not a constant force. It's just that, just think of me as just pushing it and then it goes in one direction. That's it. All right, now let's see what, I've added the force. Oh yeah, of course. Now because I have, oh, you know what? Because, no, it should add to the velocity, right? So I have the odd.update, and yeah. Oh yeah, there you go. I mean, it was just a refresh problem. All right, but let's just look at it bounce on the other end and see what happens. All right, so this bounce is correct, but keen-eyed among you would have already noted that the ball goes beyond the screen and then it sort of bounces back. Oh, that's because we forgot to take into account the radius of the ball itself. So everywhere we are looking for the, we are checking for the bounce with the width and 0. It should not be the width and 0. It should be width minus this dot radius, right? I mean, because that's where the bound is, and this should just be this dot radius, The same thing happens, let's see, minus this dot radius is equal to this dot radius. If it is less than this dot radius, then it is equal to this dot radius. The same thing happens with height. If it is height minus with dot radius, or if it is less than this dot radius. I'm going to stop saying this dot radius. This dot radius. All right. Let's see what happens now. All right. Wow, that looks much better. That looks much better, right? That looks like it's a thing. Alrighty. But you know what? In a real physics system, every time something bounces off a screen, or every time something actually moves, there's some sort of damping that is going on. Whether the damping is through friction or air resistance or whatever, some sort of damping has to happen, because if I just let it run like this, it's never going to settle back. Gravity and whatever force it has, it's just going to, keep on going. So I'm going to damp, whenever there is a bounce that is happening, I'm going to damp that velocity. What does that mean? I'm just going to say this dot velocity dot x into equal to, how much do you want to damp it by? I'm just going to arbitrarily choose 0.9, all right, on the x direction as well as on the y direction. Now let's see what happens. So every time it bounces, it loses some of its energy. Now let's see what happens. There you go. You see that settling down? Beautiful, right? Boonk. All right. So yeah, so every time it, so there is no air resistance as such, but there is, it loses energy whenever there is a bounce that is happening. Even on the x direction, it is definitely losing its energy. You don't, I don't know if you see it, but it is definitely there. All right. So that's how you do one. So that's how you do one orb. Is that it? Oh, let's just do one more thing. You see the direction of motion. I don't know what direction of motion it's having. It would be great if I could have sort of a spoke on this orb that shows the direction in which it is moving. How would I draw? Let me just draw that. All right. So what would that look like? Let's see, context dot stroke style. I'm just going to make it black for now. Black, context dot begin path, context dot move to, because a line in JavaScript is drawn by two functions. You move to a location and then you put a line to a specific location. So it moves to where? It moves to the center of the orb, which is basically this dot position dot x, comma this dot position dot y. Perfect. All right. And then what? Where does it go to? All right. Line to this dot position dot x plus this dot radius and this dot position dot y, and then I can say context dot stroke. Now let's see what happens. All right. So now we have a very primitive stroke. I mean, or a spoke being displayed on the orb itself, but it doesn't move along with the orb itself. How do we fix that? We need to have it essentially move along with the ball, or at least in the direction in which it is moving. Oh, this is going to be interesting. Why? Because I need to essentially move this to a specific location on the screen itself. All right. Oh, what do I mean by that? Essentially, if this thing is over here, I need to essentially point it at that direction on the radius itself. So it needs to have a different position altogether. It needs to have a different line to position altogether. How do I do that? I can do that by having calculating the sine and the cosine values to its new position. So I did this a long time ago in processing. So I'm just going to essentially see what I did there, and I'm going to put this over there. Just having a little bit of trouble recalling how I did the radius. All right. Yes, I think I get it. So let's say I'm going to have a variable called this dot radians, and I'm just going to say this dot radians is 0 now, and spoke line 2. All right, so this is the end position of the spoke, is equal to new point all right. So the spoke line 2 is already it's already determined. All right, so let's calculate the so let's just calculate the radian. What would the radian be? And say this dot radians. All right. I need to calculate the x and y position of the spoke line 2. Say this dot spoke line 2 dot x is equal to what? It should be this dot position dot x plus this dot radius plus math dot sine of this dot position dot x. Yeah, I mean no, this dot radians. Yeah, it should be this, and the y position would be this dot position dot y plus this dot radius but math dot cosine of radians. Is that correct? No, I think I mixed it up. This should be cos and this should be sine. So now that I have this, let's see what it looks like when it is rendered. This dot, it should just be oh. Oh no, this is no, the math seems correct. All right, the math actually does seem correct, but why is it fixed to a specific location? Oh yeah, of course it is x. I'm sorry. All right, so now you can see that it's actually only pointing to a specific direction. It's not actually moving or anything, and it also seems to be a little bit bigger than I had thought. A little bit bigger than I had imagined. I mean, the spoke is a little bit bigger than I had thought it would be, but that's fine. We'll fix that. Oh, by the way, the reason why it is not actually moving is because this dot radians is not changing. Let's change that. So let's change. Say plus is equal to 0.1. Remember, it should be a value between 0 and 2 pi. Let's see what happens. This dot radians is 0. This is the update function. Yeah, this is the update function. Of course, it's the update function. Is it increasing and I'm not seeing it, or is it too small for me to notice? I mean, I'm not sure if you can see it on your screen, but there is something that is happening. But there is something that seems to happen. All right. This dot radius and oh, sorry. As much as you hate dead, silence over this podcast, even I hate it too when I have nothing to talk about. There's obviously some error that is. Oh, hold on. Maybe there's something in the logs that I'm not seeing. No, there's nothing in the logs. This is actually pretty fine. Oh, you know what? Is it in degrees or is it in? Let me just give 10 and see what happens. So nothing happens, right? Okay. Oh, that's entirely too fast. Okay. Just going to give a constant for now and see what happens. What happens if I make it math.cos? Do you know what? I'm just going to look up something from last week's. Oh, it's a value between 0 and 360. So it's basically in degrees and not in radians. So it's a value between 0 and 360. So I'm just going to give 90 and see what happens. What am I missing? So this is x position dot x dot. Oh no, this isn't a plus. This is a multiplication. Oh my god. That's embarrassing. There you go. All right. So that, so that's, so I think that about fixes it. Okay, this dot radians. Well, that's too fast. That's too fast, but you can still see that it does. All right. Yes. So we got that fixed, but you will see that it's actually not dependent on the direction in which it's going. And number two, we just arbitrarily chose 0.1. The radians should essentially increase with the velocity, the x velocity of the orb. All right. So I'm going to make radians dependent on the velocity, on the x velocity. All right. Yeah. So, and how do we do that? I'm just going to say radians is equal to this dot velocity dot x by this dot radius. All right. Let's see what happens now. Oh no, do I have to increase it? Oh, come on. Really? Okay. Do I have to increase it? Yes, I actually do have to increase it. All right. So so there you go. So now, not only is this will the spoke change the direction in which it is going, it will also look very appropriate, meaning the rotation of the spoke matches exactly the speed in which it is going. All right. Yeah. So I think that's all I had to show for this supplementary. And basically I just wanted to create a very simple physics system where I can have such kind of a ball rolling, bouncing across the screen, and this will help us do our genetic algorithm. I'll link both of these episodes in the video, the source code for this and everything. I'll put it in the video description and everything. So thank you so much for joining me. Thank you for watching this supplementary video. If you can actually share this with your friends, like, share and subscribe to this channel, you would do me a great favor. Thank you very much.